right, so back to your notes. So here we go. Relative strengths of acids and bases. What we say are strong acids dissociate completely in water. Okay? So here, before the dissociation, this is my acid. Okay? The HA is just some random acid that I have in a container. Okay? I know it is a strong acid because once it dissociates, it dissociated into all of my H positive and my negative ion completely split apart. Do you see I have the same concentration of hydrogen ions as I had of the original acid when I started? That's how I know that it is a strong acid. Okay? If it was a weak acid or a weak base, right here, okay, here's the amount of original acid I have in the container. After it dissociates, I still have most of my what? Original acid. I only got a little bit of the H positive and the negative ion. Only a little bit of it dissociated. So then I would say that this is a weak acid. Do we see this? Now again, because I say weak acid, does that mean it's not very acidic? No, it doesn't mean that at all. All we mean in terms of strong and weak is strong, it dissociated completely. All of it broke apart. Right? You can see here, all of it broke apart. And then if it's weak, we can see that only a little bit of it broke apart. Okay? So again, do not confuse concentration with strength. Okay? A lemon is definitely more of a concentrated acid than an orange is. Right? Okay. But if we pretended like the peeling was hydrogen ions, then we would see that the lemon would be considered the weak acid and the orange would be considered the strong acid. Okay. All right. So the strong acids, you need to memorize these 6. It will make your life A, so much easier, and B, I expect you to have them memorized. Period. Hint, hint, wink, wink. Makes a great quiz. List the 6 strong acids. That's real easy to grade. Okay. So, HCl, HBr, HI. Notice all 3 of these are in column what on the periodic table? 17. They're in column 17 on the periodic table. Notice HF is not considered to be a what? Strong acid. Okay? That's because the bond between hydrogen and fluorine is very, very strong. So therefore, if they are bonded tightly together, is that hydrogen going to be able to easily remove? No. So HF is considered to be a weak acid. Now, just a little bit about this weak acid. This weak acid will eat through bone in a very short amount of time. So is it weak? No. So again, don't confuse that we're calling it a weak acid, meaning it's harmless. Okay? Hydrofluoric acid is definitely not harmless. Not even close to it. Okay? It's just because this bond is really strong, so this hydrogen doesn't want to remove itself, so it's weak. It doesn't dissociate. It doesn't break apart. Okay? So, HCl, HBr, HI, nitric acid, HNO3, sulfuric acid, H2SO4, and perfluoric acid, HClO4. Okay. Some people, we'll do a sometimes strong here. There are some people that consider fluoric acid strong, which would be HClO3.
If we forget like one of the other ones on our quiz and put that one, will it count? Because that was a
I
little
feel
bit
like this should be more of like a
bonus.
Yeah.
Well, that's a little bit easier to remember than like H2SO4.
So these 6, HCl, HBr, HI, HNO3, H2SO4, HClO4. Those are your 6 strong acids, and you need to remember them. Okay? Same ones we did last year. Promise.
Yeah.
So if you look here again, here's my HF, my HCl, my HBr, and my HI. This right here is what we call bond strength. So it determines the strength of the bond. Okay? We see my HI, my HBr, my HCl, my HF. Which one of these has the strongest bond?
Yeah.
The HF, right? It's a 565. So this is why HF is considered to be a weak acid, but my HCl, my HCr, and my HI are strong because they have weaker bonds. So if we have a strong acid, that means we have weak bonds. Smells like oranges and lemons in here now. It is refreshing. I like it. Maybe I should just peel lemons and oranges at the beginning of every day.
Oh, yeah, that's what kind of blessing.
It does. She ain't lying.
All right. The more oxygen that is present in an oxyacid, okay? What is an oxyacid? What's it sound like? What's oxy make you think of? Oxygen. So an oxyacid is an acid that has oxygen, okay? So don't let the term confuse you, okay? The more oxygen it is, the stronger the acid is. So the more oxygens I put in there, the stronger the acid is going to be. So if I have 2 oxygens in an oxyacid versus 3 oxygens in an oxyacid, which one's going to be stronger? The one with 3. Now again, the fact that it's strong just means it what? Dissociates. Okay, that it breaks apart completely. Okay, notice this is a trend, not an explanation. So you could not say on an exam or a test, if I gave you the choice between 2 acids and said which one is stronger, you couldn't say, well, like let's say I told you to choose between H2SO3 versus H2SO4. Okay, which one are you going to choose for the stronger acid? H2SO4. And you're going to choose it because why? It has more oxygens. You cannot write for your explanation because H2SO4 has more oxygens. Okay? That is not an explanation. What you would have to say is oxygen is very electronegative. Okay? What does electronegative mean? There you go. It wants the electrons. Okay? So it attracts all of the electrons when it's bonded to a hydrogen. Okay. So the more oxygens I add, what happens?
The less electrons hydrogen has.
There you go. The more oxygens I add, the less electrons, okay, hydrogen has. So that makes the bond between the oxygens and the hydrogens very what? Weak. Okay? It makes the bond weak. What do we know happens when we have weak bonds? It breaks apart easier. So then it takes less energy to break the bond, so the acid dissociates more easily. Okay. Your explanation would need to talk about this. It would need to talk about the fact that oxygen is electronegative. So when we add more oxygens, okay, it pulls more of the electrons away from hydrogen. It makes the bond weak, so it's easier to break the hydrogen off and dissociate. Do we see this? Okay. You cannot say, I'm going to say one more time, you cannot say because the more oxygen, the stronger the acid. It's not considered a good explanation. So, let's look at here. Okay. Here is our chloric acid, my HClO4. Okay. Here's my chloric acid, HClO3. Here's my chlorous acid, HClO2. And here's my hypochlorous acid, HClO. Okay. Now, which one of these 4, 1, 2, 3, or 4, is going to be the strongest acid?
Or
my HClO4. Alright? Why? Because these three oxygens here are doing what? They're pulling all of the electrons this way. Notice we still have the effect up here, alright? We've still got it here, we've still got it here, but the more oxygens that we add, what's happening to the effect? It's getting greater. We're pulling more and more of those electrons. So that means this hydrogen is going to be very easy to remove. Okay. This is more of what they would ask you on the AP exam as far as like circling the hydrogen that's going to leave. Something like that. Should be pretty simple. Now, remember those K's we talked about? Everybody remember K? Big K? Alright. What's the formula for big K? That's my equilibrium constant. Products over reactants, right? It's the concentration of your products over the concentration of your reactants. So now, we've done Kc, we've done Kp, we've done Ksp. Now we're going to throw in two more. We're going to start talking about Ka and Kb. Okay? Guess what? It's the same chemical formula. It is still concentration of products over concentration of reactants. Nothing has changed. But now we just put an A to show it's the equilibrium constant of an acid. Or we put B to show that it's the equilibrium constant of a base. You are on it today, Spencer. I'm impressed. So make sure, okay, you don't let the K's confuse you. They're still concentration of products over reactants. If this breaks apart completely into H positive plus ClO4 negative, okay, should my Ka be large or small? It should be large. Why should it be large? Okay. Since it broke apart completely, do I have very much reactant left? No. Okay? I have very little reactant, so this number is going to be very small. Okay? Since it broke apart completely, do I have a lot of product left over? Yes. So my number on top should be very large. When I take a large number and divide it by a small number, what kind of number am I going to get? A big one. So for a strong acid, my Ka value should be large. If it's a weak acid, am I going to get very much product? No. Okay? I wouldn't get a lot of product. So I would get very little product, and I would still be left with a lot of reactant, correct? So if it is a weak acid, then my Ka should be very what? Small. Do we see that? I'm going to erase this right quick so we can do the chart now because I wrote all over my board. So if we look at this, let's look at your HClO. Look at the Ka value of your HClO. It's a very what number?
Small.
Small number. So that lets me know that HClO is what kind of acid? Weak. Okay. Whereas if I scroll up, okay, here's my HClO4, that's my perchloric acid. Look at its Ka value. It just went ahead and wrote large. It's approximately something times 10 to the 7th. This is a really big number. So that lets me know that my perchloric acid is very strong. All right, this will be the last concept we do today. And we'll wrap it up. All right, the stronger the acid. Oh, let's go over this right quick. So we know what our strong acids are. There's 6 of them. Here's how you know your strong bases. Okay? They are the hydroxides or the oxides. Hydroxide is what? OH negative, okay? Or the oxides, meaning they're just bonded to the oxygen, alright? Of group 1 and group 2 metals on the periodic table except magnesium and beryllium. So Mg, so let's write down the strong ones, okay? LiOH is strong from group 1. NaOH is strong from group 1. Everything in group 1 is strong, okay? KOH, I'm just going straight down group 1 in the periodic table.
Please excuse interruption. Any student interested in playing soccer, you need to see Coach Dean in his room at break. Any student interested in playing soccer, see Coach Dean in his room at break.
Okay. So then if we look at group 2 hydroxides, the first two, so it should be easy to remember, your beryllium and your magnesium are considered weak bases. That must mean the bond between them is very what? Strong. Okay, the bond between them is strong. So Ca, and we would write that as OH2 is strong. SrOH2 is strong. Ba, OH2 is strong. And Ra, OH2. Alright, the stronger the acid, the weaker its conjugate base, and the opposite is also true. The stronger the base, the weaker the conjugate acid. So, let's look at this. If I take HClO4 and I break it apart, I would get what? Alright. This is my acid. Where's my conjugate base? What does the acid do in the solution? Gives away the hydrogen. So now my ClO4 negative becomes my conjugate base. We know that ClO4 is what type of acid? Strong acid. So I would say this ClO4 negative as a base is very what? Weak.
So if you don't have a base on your reactant side, you wouldn't label conjugate acid for your formula.
You could say this is the conjugate acid. That is the conjugate acid. Alright, we'll stop there for today.